Today we are going to study the phenomenon of diffusion of gases. The diffusion of gases is possible if the concentration of gas in different regions is different. If the concentration is same in the container, then there is no transport of molecules from one region to the other region. This phenomenon of diffusion of gases is basically related with the different concentration in different regions. Then what will happen? The molecules of the gases from higher concentration region will move to the lower concentration region, and this phenomena is called as the phenomena of diffusion, and this is basically due to the transport of mass. Now let us consider the diagram shown here. Now here what is shown in this diagram, as usual we have considered three layers of the gas. Layer A, in which the number of gas molecules present are n. Then we have considered layer B and one more layer, that is C. And here we have considered that the number of gas molecules in layer in contact with X, here we consider n is equal to 0. And as we move along the y-axis, what will happen? The number of molecules will go on increasing. Means if we consider the three layers, layer C, layer A and layer B, the number of gas molecules present in these layers are different. Here again we have considered that these three layers are separated through distance lambda, which is the mean free path of the gas molecules. Means there is no collision take place over the distance lambda. So these three layers are separated through distance lambda, which is the mean free path of the gas molecules. Now suppose that the number of molecules in layer A is n, and if dN by dy is the gradient, concentration gradient along the y-axis. What is the meaning? If we move along y-axis, what will happen? The number of molecules in layer go on increasing. If lambda is the mean free path and dN by dy is the concentration gradient, the number of molecules in layer B will be n plus lambda dN by dy. Similarly, the number of molecules in layer C will be less by an amount lambda dN by dy. So we have written here n minus lambda dN by dy. See, compare the three figures. In first one we have considered phi minus lambda dV by dy. In thermal conductivity, we have considered as theta minus lambda d theta by dy, because theta is the variable in second case. Velocity is the variable in first case, that is viscosity. And in this case, there is the gradient in concentration. Concentration is different in different layers. So the concentration gradient is dN by dy. So accordingly, we have calculated the number of molecules in layer A, that is we have taken it as n. So obviously the number of molecules in layer B will be more than this n, and that is n plus lambda dN by dy. Similarly, the number of molecules in layer C will be less, therefore that is n minus lambda dN by dy. Now go to the derivation part. The number of molecules crossing layer A upwards or downwards per unit area will be n C bar by 6. So n C bar by 6 is the average number of molecules crossing either in the downward direction or in the upward direction. So number of molecules crossing layer A per unit area per second will be c bar by 6 n plus lambda dn by dy. Here what this n represents? Here n represents the concentration of gas molecules. Similarly, the number of molecules transferring layer A in the upward direction from layer C will be c bar by 6 n minus lambda dn by dy. Therefore, we calculate net transfer of molecules per unit area per second. Layer A will be c bar by 6 n plus lambda dn by dy minus c bar by 6 n minus lambda dn by dy. So we simplify the equation. So net number of molecules crossing layer A per unit area per second will be, so see, c bar by 6 taken common, n plus lambda dn by dy. This is the term coming from layer B, minus n minus lambda dn by dy. This is the term coming from the molecules crossing from the layer C. So after simplification we get c bar by 6. This n get cancelled. This minus becomes plus. So we get plus lambda dn by dy. And this lambda dn by dy, that is 2 times lambda dn by dy. Or we get c bar by 3. This 2, here we get 3. So c bar by 3 dn by dy into lambda. Now the coefficient of diffusion is defined as the number of molecules crossing per unit area per second divided by concentration gradient. So d is equal to d, that is coefficient of diffusion, is equal to the number of molecules crossing per unit area per second we have calculated in equation 1. So that is substituted here, c bar by 3 dn by dy lambda, and the concentration gradient is dn by dy. So this dn by dy get cancelled and we get d is equal to 1/3 c bar lambda. Now I divide and multiply this equation by a row because I want to introduce the term viscosity. So d is equal to 1/3 as it is, multiplying by row and dividing by row, c bar lambda as it is. So what do we get? This 1/3 rho c bar lambda, that is nothing but the coefficient of viscosity which we have obtained previously. So we write finally coefficient of diffusion d is equal to eta upon rho. Remember this relation for multiple choice questions. So this is the relation between the coefficient of viscosity and diffusion of the gas. So diffusion of gas d is equal to eta upon rho. So this is the relation between the coefficient of viscosity and the density of the gas rho. Now the remarks. As we have seen that the average velocity of the gas, root mean square velocity of the gas molecules, is directly proportional to root T. Therefore, the D is also proportional to root T. From this relation, here we have D is equal to 1/3 c bar lambda. As c bar is proportional to root T, this D is also proportional to root T. So this is the first point. And secondly, this D is inversely proportional to rho. D is inversely proportional to rho. What is the meaning? As we go on increasing the temperature, the coefficient of diffusion also increases. But if we go on increasing the density, the rho, the coefficient of diffusion decreases.
If you like this video, don't forget to subscribe, comment and share this video with your friends. Thank you. for watching.